Hello, welcome all of you. So, we are at module 47 of week 8 and this will be the last module of this week, and as I mentioned in the first video of this week, I said we will have one more week of lectures to cover some of the topics that students have given feedback about, specifically related to number representations and arithmetic circuits. So, in this concluding module of this week, what we will do is we will connect all the things that we have seen so far. In the past 4 modules, we looked at what pipelining is, what interleaving is, and so on. But in the last module, we looked at what are the different intricacies when we involve blocking versus non-blocking statements. So, what I want to do in this class is connect pipelining to the way we model circuits in Verilog. So, this will be the concluding module for this week. So, let us take a step back and look at the GCD machine that we designed. So, the GCD machine that we designed was actually quite nice in some way. So, first of all, we actually used fairly simple concepts. So, we started with the algorithm and then we went and did what is called unrolling the loop. So, there was a while loop in it and we figured out that we need a structure which will keep the loop iterating, and we had a state machine which took care of how things were done. And finally, what we did is we said we identified the basic computing structure and we had a sequence which was running through it. So, something like that where we take a problem and divide that into a distinct data path and a control path, such a design would be called RTL design. So, this is something that you may see in job postings and whatnot. So, RTL design essentially means register transfer level design. So, the implication is that you actually start looking at basic modules, and these basic modules in turn are connected. So, you have basic registers and you have various arithmetic units and logic units and so on, which are all connected together, which form the data path, and a control machine or a state machine which controls the sequence of these events. So, such a level of design is called RTL, and we are going to see RTL models for pipeline circuits in this lecture. So, the chief characteristics of RTL design is that it is a perfect balance between abstraction versus structure. So, we could go all the way down and do various things, but then if you notice the subtractor that we designed and the comparator that we designed was not in terms of basic gates. So, we used the operator minus for subtraction, and for comparison we just compared 4 bits with 4 bits and so on. So, such a level of design where we do not bother with the finer details of the actual hardware, but bother with the abstraction or the programmer's intent. So, this is a perfect balance that you get from RTL design. So, what we do in RTL design is we declare the wires and regs so that we know all the connectivities that we need, and we have Verilog statements that imply the data path elements and the registers. We also identify all the multiplexers and buses that are needed. So, even the GCD example, if you remember, we had 2 multiplexers to choose where the inputs are supposed to come from. We decided on a clocking mechanism, and we also identified the register width. So, by register width I meant, so in the GCD problem we said we will look at GCD of 8 bit to 8 bit numbers. So, the implication of that is the multiplexer, the subtractor, the comparator, all of them were supposed to be 8 bits. So, once you identify the structure, we need to put those parameters in and take it all the way down. So, these are the chief characteristics of what is called the RTL design. So, let us look at various examples of data flow modeling. So, let us look at this picture here and the corresponding Verilog description. So, I am not providing the complete Verilog description, we are only seeing the part of the Verilog description. So, let us say we have input 3:0 ABC and we have a read 7:0 D, and we have assigned D equals A into B plus C. So, what this would mean is we are looking at D being assigned A times B plus C. So, A times B is a 4 bit number multiplied by another 4 bit number, the result is a 8 bit number to which we are adding a 4 bit number. So, the result is a 8 bit number. So, D is actually a 8 bit number, and if you wrote something like this, so forget the declarations, if we had anything like assign D equals A times B plus C, then the implication is we have A, B, C which are the inputs and D is the output, and A times B. So there are tools which are called synthesis tools, which can look at this line of code, understand that star means multiplication, and actually throw in a multiplier there, and also understand that plus means an addition and throw in an adder there. So this plus is adder and this cross is multiplier. You could infer something like this by writing a line of code like this. So you could also go and write this whole thing in a structural manner. So by that, for the adder you may actually use a ripple carry adder, for a multiplier you may come up with your own way of doing multiplication of two numbers and so on. But if you do that, the programmer's intent is buried inside lots of lines of code, whereas this is very clean and many tools can immediately understand that you are looking for multiplication and addition. So forget some of the definitions and so on. So there is some mismatch in capital letters versus lowercase letters and whatnot. So the intent is not about the syntax here, but about what is the inference from the Verilog that we are writing. So for instance, all of these must have been small case letters and whatnot. So let's ignore that for a while. So this is called data flow. Now we could do something else. So let's look at the thing on the left side. Always at A comma B, AB is A star B. Always at passage of clock, D is AB plus C. So if you notice, this A and B are inputs, and we did always at A comma B, which means any change in any of the bits of A comma B will result in this always block being triggered, which means the multiplier, if there is any change in input of the multiplier, there will be an output change in the output of the multiplier. So this star means multiply, so AB is A times B infers this part of the circuit where you have A and B as inputs and there is a multiplier. This wire here is essentially AB, and what we have here is, here we have D equals AB plus C. So this is AB added to C should give D, and the reason why D is a register is because we have always add passage of clock, which means this D will be a 8-bit register and there are 8 lines going out of the adder which all get registered in D. So this is the hardware that will be inferred if you write code like this, and you can see that this is combinational in nature and this is sequential, and we have adopted all the policies that there is a blocking equal to here and a non-blocking equal to here and so on. So it's fairly easy to understand what this is doing, but more importantly, from a, if you want to think about it as a software, what you are actually doing is D of I is A of I into B of I plus C of I. So you are taking inputs which are all given at one instant of time, that is what this I means. So this I is not subscript within A, this A of I is time. So at time I, whatever A, B and C, if they are all kept stable, then it takes those inputs A and B, multiply, add it with C, and that will go as input of this flip flop here. In the next cycle, this value will get into the register. When the next clock pulse comes in, it will go into the register. So the hardware inferred is essentially this. So the implications are that addition and multiplication are cascaded, because we have one combinational blob followed by another combinational blob. So we have those two cascaded, and if I want to look at the rate at which I can give these inputs, this is from global inputs to flip flop. So this is input to flip flop. The longest path in that will be through the multiplier and the adder. So the maximum delay through this combinational logic is propagation delay of addition plus propagation delay of multiplication. So after that delay, the register can actually register the data, but meanwhile you want to keep the input stable so that this will not change or upset the this flip flop. So the next clock pulse we have to give only after T add plus T mult. So remember, we did this timing sequential circuit timing analysis in probably week 5, I believe. So this operation takes one cycle and you can give one set of inputs in every clock cycle. So all of that is probably very clear to you. Let us now look at the different kind of a statement. So here what we have done is, always at passage of clock, D equals A times B plus C is put inside the always statement. So you could write something like this. This is still in some sense relatively straightforward. You have A times B plus C, So, if you write a single statement like that, Verilog, both the simulators and the synthesis tools. So, simulators go and show you waveforms so that you can go check everything is correct and so on, and synthesis tools actually take this, infer gates for you, and can actually spit out a net list. So, D equals A times B plus C is a template that these tools can understand, and it can infer the same hardware as the previous one. So, this is essentially a multiplier followed by an adder followed by a register, and you can start seeing why it should have a register and why this A into B itself is not registered. So, if you look at this one, right, only the result of this addition is registered, not the result of the multiplication followed by the result of the addition. So, this requires only one level of circuit, and what we have here is essentially a one stage pipeline, and remember, one stage pipeline is no different from a combinational circuit in terms of overall latency. You still have to wait for one full clock cycle. Now, let us look at another model. So, this model is always at passage of clock. AB is A times B, D is AB plus C. So, let us say we wrote something like this, AB is A times B and D non-blocking equals AB plus C. So, take a while and think about what it should really be inferring first. So, if you notice, AB and D are on the left side and both of them are in passage of clock, which means AB will be registered, which means the result of the multiplication will get registered and the result of the addition will also get registered. So, now go and think about what will be the overall circuit. So, once you are done with that, come back to this. This would be the hardware, A and B would be multiplied and that would be stored in a register AB, and C would be multiplied with the registered value of AB and that would give a D. So, the first thing that you have to now go and think about is what is the circuit really doing, right? Is it going to be correct, and if it is not going to be correct, what is the issue with it? So, a quick clue is that this is not correct, go and think about why, and then come back to the next slide. So, let us see why it is not correct. So, let us see AB equals A into B and D equals AB plus C. The first thing is there is a register inferred for AB because it is inside passage of clock. There is also a register inferred for D because there is a passage of clock. So, you have two registers and this multiplication will give you this and adder will give you this. So, it looks like whatever code we wrote, the hardware that is inferred is actually correct, but is this capturing the intent of the programmer? So, the problem with the model is essentially this: the multiplier will work on the current A and B that is given, but adder works on the current C and previous AB. So, you go and look at the picture. If you go and look at what the adder is adding, let us say at some point I gave A, B and C which all changed together at time instant I. Let us say I gave a fresh set of inputs, A of I, B of I and C of I. These are the inputs that I have given at time instance I. This multiplier will be looking at A of I and B of I, and you give C of I here, but this adder will take C of I and AB of I minus 1, because this is a register, it is holding the previous value of the multiplication of A and B. So, it takes AB of I minus 1 and C of I and adds it. This is a problem because we wanted A of the current input A and B multiplied together and added to C. However, we are adding the previous value of A and B's product with current value of C. If this is not the programmer's intent, then this hardware is incorrect. So, in this case we wanted to do AB plus C, and this is doing A of I minus 1 times B of I minus 1 plus C of I, and this is not correct. This is not what the intent was. So, from a simulation point of view, let us see why this is consistent first of all. So, the hardware that we saw was the picture that I showed earlier. Let us see from a simulation perspective whether this is supposed to be correct. So, AB was a non-blocking statement. So, AB non-blocking equals A times B. So, it will not be updated until a new timing control comes through. So, remember, if you go back to this Verilog code here, right. So, you go and look at all the write sides, the write sides will all be calculated first. So, when a new clock comes, it will take current A, current B, multiply it, you keep the result aside to assign to AB in the future. Then you take current AB and C, add them, and put it for D, but the current value of AB that you have is something that you had in the previous cycle. So, that is the problem. So, AB is a non-blocking statement, it is not updated till a new timing control comes through. So, D uses the value of AB, but it is not updated immediately. So, the simulation and synthesis view that we have for this is correct. So, essentially the model that we have is wrong. The synthesis and simulation matches in what they are showing, and the model that we have is incorrect for the problem that we started with. Let us look at another Verilog model. So, in fact, if you look at this, what you have is this is not a properly formed, it is not a well formed pipeline circuit. So, this problem with this is it is not a well formed pipeline circuit, because A and B go through 2 levels of registers, whereas C goes through only 1 level of register. So, there is a problem in the path from C to D. So, I cannot put a new flip flop here on the path from C to D, because that will also increase the path of the flip flop from the number of flip flops from A to D. So, what that means is in this path from C to the adder, I should put a flip flop. In that case, what happens is it makes it a well formed pipeline circuit, and the next Verilog model is essentially that. So, let us look at that Verilog model. Always at passage of clock, AB is A times B, and we have something called C temp. We say C temp is non blocking equals C, and D non blocking equals AB plus C temp. So, the key thing is you have C temp here and not C. So, let us see what the hardware inferred for that would be. So, again the Verilog code is shown in the right bottom here. So, AB, C temp and D are all on the left side in an always statement which has a passage of clock, which means AB, C temp and D will all infer flip flops or registers. So, AB is a register, C temp is a register and D is a register. And what are the operations that we need? We need a multiplier and we need an adder. So, there is a multiplier and there is an adder. Now, let us go and look at how these things get connected. So, the product of A and B should be given as input to AB. So, the product of A and B is given as input to AB. C is given as it is as input to C temp. So, we give C as it is as input to C temp, and AB and C temp should have an adder in between. So, the addition of this should go to D. So, that is what you have here, AB and C temp are added together and the addition goes to D. So, what we have is we have taken this always block and inferred this piece of logic. Now, let us see whether this is a well formed pipeline circuit. So, from A to D there are 2 registers or 2 levels of flip flops, from B to D again there are 2 levels, from C to D again there are 2 levels. So, for all the intermediate levels also there is no mismatch. So, if you go and look at AB itself, AB, so if I go and look at the wire AB, it is after 1 level, right. So, there is no mismatch anywhere else. From all the inputs to your outputs we have 2 levels. So, this is a 2-stage pipeline and this is a well formed pipeline. So, the analysis, so again the Verilog code is shown in the right bottom. Analysis of the model shows that the new reg C temp copies C, all the regs A, B, C temp and D get a register, and when AB is computed, C is just copied to C temp, and adder always looks at the previous value of AB and C temp. All the inputs pass through the same number of registers. So, the equivalent thing that we have is we are looking at, so if I go and give inputs I, it is going to take 2 cycles or a latency of 2 cycles to come to the output. So, the D input that you are going to see here is actually looking at AB of I minus 1 plus C temp of I minus 1, which is actually equivalent to C of I minus 1. So, the equivalent code would have, in software you would have written it as D is A of I minus 1 times B of I minus 1 plus C of I minus 1, which is perfectly fine as long as all the inputs that we are having are supposed to be coming from the same instant, only that the output is coming 2 cycles late. That is something that you have to watch out for, that is all. From a simulation point of view also this is perfect, because you go and look at all the right side, you compute the current, you take the current A and B, multiply it, but you want to give it in the future. You take the current C, whatever C is storing, and put it in C temp, but whatever AB and C temp are storing right now, you add them and put it in D. So, we evaluate the right side first, A B, that A times B should be given to A B in the future, you do not do it right away. Whatever value of C should be given to C temp in the future, you do not give it right away, but whatever value of A B and C temp are right now, you add them and assign it to D in the future, and the future will come when this always block is suspended, as in all the assignments are evaluated, all the right sides are evaluated. Now we are ready to go and assign to the left sides. So, all of them will have a consistent view. So, a little more analysis, unlike the model with the blocking statements, the results are not available immediately. I hope that is something that you got from this module, from this week's modules. The clock can now actually be the maximum of T add comma T mult instead of T add plus T mult. So, T add plus T mult, as long as both are positive, maximum of T add comma T mult is guaranteed to be less than or equal to T add plus T mult. Essentially what we have is, we have a clock that can run faster, we can supply data once every cycle, but and you also get the results once every cycle except for the very first cycle. So, essentially there is a latency of 2 cycles, there is a throughput of one input that is being processed, one set of inputs that is being processed every cycle. So, this is what we call pipelining. When the multiplier is working on the current set, the adder is evaluating the results from the previous set. So, the adder is getting a consistent set of inputs, but it is operating on the previous thing that you gave. So, thus the data path elements are actually working in tandem, and this is what we call pipelining. So, the data is essentially marching through from the in some sense left side to the right side, or from the primary inputs to the output register under the control of the clock, and this is facilitated by small combinational blocks that we have put in between, namely the multiplier and adder. So, in terms of a picture, usually for pipelining people draw what is called a cloud diagram. So, let us say this is the block A, which could be the multiplier, and this is block B, which could be the adder. Then without pipeline, the set of inputs going through some combinational logic going through this would have a delay of TA plus TB. So, let us say this is some combinational logic, this is some other combinational logic, then a set of inputs that is firing from here will need TA plus TB time plus setup time here plus clock to Q delay here to settle down. Whereas, the moment you put a set of flip flops in between, then this to this flop is TA plus setup time plus clock to Q delay here, and this to this would have been clock to Q delay here plus TB plus setup time. If clock to Q and setup time are the same, then we are essentially looking at the rate at which this whole circuit can run is maximum of TA comma TB, not TA plus TB. So, this is a key thing, this is the most important thing about pipelining. The moment you start putting pipeline registers in between, you are cutting down the combinational delay and you are enabling faster clock. So, you get better delay, but you get at the cost of what is called latency. Latency is the cost with which you are using the pipeline. So, the results are not going to be in the current cycle itself, you are going to take 2 cycles, or if it is a 3-stage pipeline it will be 3 cycles and so on. And if you start putting in more and more pipeline registers, the latency will become higher and higher. We also discussed that parallel processing and interleaving are very 2 different alternatives with which you can do similar things. So, you can achieve the performance of pipeline circuits by also doing either interleaving or by parallelizing. So, latency is important for circuits like microprocessors. So, processors like CPUs and so on, latency is really important, because when a result comes, when a set of inputs come in, how quickly the result comes out in terms of cycles, this is important for microprocessors, and most of the operations in fact inside a CPU needs to finish within 1 clock cycle. Things like addition, multiplication, logical AND, logical OR and so on, you would want all of them to finish within 1 cycle. So, which means what you have to do is you have to design a circuit that is really fast. Remember, if you are giving only 1 cycle to do addition or multiplication, then we cannot say I will pipeline it and I will get the results after 5 cycles. We need the result in 1 cycle, the whole thing should be combinational and it should be fast enough to accommodate, let us say 1 nanosecond delay. So, that is all you can get for a 1 gigahertz clock that is used for a processor. In fact, if you are using a 3 gigahertz or a 4 gigahertz processor, you are looking at either 0.33 nanoseconds or 0.25 nanoseconds to implement the whole adder. so or multiplier and whatnot. So latency is really important for microprocessors, whereas if you are going to look at DSP, digital signal processing or anything like that, throughput is a lot more important. You are looking at what is the rate at which I can process video frames, or what is the rate at which let us say spoken waveforms are processed and so on. So usually you are acquiring real time data and you are processing it. Latency may not be a big issue, however throughput, I should be able to process everything that's coming in as input, and I should be able to take one frame after another every so many time units and so on. So for such things like DSP, throughput is a lot more important than latency. So let us look at a simple example in signal processing called convolution. So if you are in the 4th semester, you might have learned what convolution is. So it's to simplify it is essentially as simple as this. You take A of I and B of I. In this case, we are looking at different values, not time, A of I into B of I, and I equals 0 to width. So this is essentially equal to multiply, add and accumulate, right. So we are multiplying A of I and B of I, that is the multiply, and we are adding for several values of I, and we are accumulating the results in C. So this is usually called a MAC operation, and W is usually the window size, and the result is eventually stored in C. So the sample set is essentially a moving window and can be arriving in real time. So if you change I equal to 0 to width, it's the, let us say 0, so whatever the width of the window is, you are processing that, and then you move the window and then you process this once more and so on. That is what convolution does. So if you want to do hardware directly, right, you may actually end up something like this. So B is the set of inputs that is coming through, and let us say we are doing convolution over a window of size 4, right. So 0 to 3 is a window of size 4, you may end up doing something like this. So A of 0, so you get B, which is a set of coefficients, and we pass them, sorry, B is the data that is coming in, A is a set of coefficients. So B is real time data that is coming in, so it is coming one sample every clock cycle, and so let us say 0th time instance it is here, all these flip flops have incorrect values, at 1 it will be here, at 2 it will be here, at 3 it will be here. So at time step 3, B of 0 would be here, B of 1 would be here, B of 2 would be here, and B of 3 would be here, and when you take the product of those, you have multipliers for those and you have an adder for that. If you go and look at the combinational delay, right, so you are looking at what is coming from the flip flops through the combinational logic. Let us say even if I put a flip flop here, then I have a multiplier and an adder in the longest path. So one way to break that is to be able to do something like this. So AB is A times B, C temp is AB plus C temp. This is what we have been seeing all along, right. A times B, and we are adding with C temp, and we are putting the result back in C temp itself. Finally we are assigning C to be equal to C temp. So the hardware inferred would be something like this. So if we go and look at this, AB is a register, C temp is a register. So we have a register called AB, we have a register called C temp. So we have a multiplier and an adder which feeds into C temp and AB respectively. If A and B are going to come from circular buffers, this multiplier will take one set of values at a time. So a circular buffer is nothing but a set of values that are in a ring, right. So this set of values is for A because we are looking at only the coefficients. This set of values is for B because it is supposed to come from the external world. You take one at a time from here and here, multiply that, put the result here, and take the previous value of C temp, add it to the AB, that will give you the next value of C temp. Once you do that, then this buffer rotates by one step, this rotates by one step, that gives you a new input along with a new coefficient. And if you keep doing this, this is equivalent to doing C equals C plus A of I into B of I. So a pipeline implementation is as simple as that. So if you go and look at this one, this assign C equals to C temp, so there must be an assign here, assign C equals to C temp is combinational, all it is doing is it is tapping the register called C temp and giving it to the external world. This brings me to the end of week 8, so we are at the end of module 47. So far what we have done in this week is we started with the notion of pipelining. Remember, pipeline is an acyclic circuit, and which means there is no feedback path from any register to any other register. There is always, in some sense, you can draw the picture from left to right or from top to bottom and so on without having to go back in the reverse. And once you have such a circuit, then it is nice, it has a lot of interesting properties. So, we looked at what is a latency, what is throughput, and we also looked at what is a k-stage pipeline and what are the careful things that we need to do when we design a k-stage pipeline. And then we looked at a whole lot of Verilog and the implications of equal to versus blocking equal to statement versus non-blocking equal assignment statement. So, once you understood all the implications of that, the pipelining using Verilog becomes much more easier. So, this brings me to the end of week 8. The assignments in this week, as I mentioned in the beginning of the course, are slightly lagging behind whatever is there in the course otherwise. So, the Verilog assignments that you are going to see in this week are going to be based on whatever you have seen till week 7, not involving the current week's lectures. So, thank you, and I will see you in the next week. So, whatever I cover in the next week will, so I will put everything together and give a complete overview of whatever we have seen in the course, and I will also cover arithmetic circuits and number representations in the next week. So, thank you, and I will see you next week. Bye bye.